So you've heard all about Input Shaper, but you don't want to mess with configuring firmware to give it a try? This video's just for you. Hello everyone, Chris here, and we're going to continue on with our Input Shaper series today, but we're going to do it in just a little bit different fashion. If there's one thing that I've heard a lot over the years about 3D printing, it's the fact that users are comfortable with the hardware aspect of this hobby, but maybe not so much the software or the firmware. And if you've been watching the Input Shaper series, you realize that sometimes you have to get your hands dirty in the firmware to enable a lot of these cool new features. And that's exactly where GH Enterprise comes in, with their Smart Shaper Silent Step Stick. It's a driver that allows you to use input shaping at the hardware level. No messy firmware configuration needed. And it works just like any other replaceable silent step stick, just with a few tricky features that you can configure in G-code to get everything set up. And in my opinion, if you're going to use something like Input Shaper, it's probably best at the driver level. Now, we're not quite there yet, but if we continue to see more and more features like this, you'll probably see companies like Trinamic integrate it all in one. But we'll see. Maybe that's a prediction for the future. Let's get started just by taking a look at their Silent Step Stick, what it's all about, and then we'll move to getting it installed and figure out how to use it. So here's our GH Smart Shaper Silent Step Stick. Now, Silent Step Stick is a term for these types of boards. It's what we've been used to for many years now. But it's an all-in-one board, replaceable driver that you can use on most 3D printer boards. Now, we'll talk more about compatibility in just a moment, but actually, what are you getting when you buy one of these drivers? The driver chip on this module is a TMC 2225. Now, the 2225 is just a little different package. It has a few different specs than a 2208, but at heart, all the things we care about, it's exactly like a 2208. And remember, with a 2208, you can talk to them via UART, just like you can in 2209. You get a lot of the same features that you would with the 2209, but you don't get stall guard. Stall guard is what enables sensorless homing. So if you have sensorless homing, this 2225 is not going to work for you currently. We'll see if they come out with more options in the future. But this is going to be a great upgrade if you want to upgrade to some silent drivers and also implement that Input Shaper feature. And that's what this little chip does right here. That's the chip that you're going to be able to communicate with. Even if you don't want to use UART mode, you can do it in step-dir mode. But this handles all of that input shaping goodness. So basically, at the heart of this, it's just a silent step stick with a Trinamic driver on it. But there's a couple things you need to know. Remember, I just said this before, this is a 2225. It has a lot of the same features as a 2208, so you will not get sensorless homing like you do on a 2209. Now, you can talk to this driver either in step-dir mode or standalone mode. You don't have to have a smart board. Or you can use UART for things like current changes. You can use G-code to make changes on that chip. So that's all intact. But the really cool part about this driver is the fact that you can communicate with it in such a way to set up that Input Shaper mode. And that's what I find really intriguing here. GH has done this in such a way that they can write out a start G-code to set up that Input Shaper for certain frequencies and models by doing a series of movements. And they've given you this calculator here online so you can spit that G-code out and then add it to every one of your prints to set up your driver right before each print. It's very quick to do. It's just a couple of quick movements, and then you're ready to start your print with that Input Shaper enabled. It is important to mention they only support Cartesian and Core XY right at the moment, but I'm sure they will be adding things like Delta very soon. They also have several shaping algorithms like you saw in our previous input shaping videos. Most of the time I just go to MZV, but definitely try out a couple to see which one's for you. So no matter what mode you want to use them in, UART or standalone, you can communicate with them with those short movements in the G-code to be able to configure them. It is volatile memory, so every time you turn the printer off, you're going to have to set it again with that G-code, but it's just easy enough to put that G-code in your start script so you run it before every print. It's very fast to do. This is a very ingenious idea to be able to communicate with that chip, And I think the only missing part here is to be able to communicate with that chip via G-code commands. But they're already working on a branch of Marlin to do just that. I'm excited to see how that's going to work out. Now, you can use these on most 3D printers, but you do need replaceable drivers on your main board. So I don't want to leave out that part. Let me show you the difference real quick. So this is an SKR2 board from Big Tree Tech. This is very common, what you see nowadays, maybe a little higher end board than some, but you see all these step stick modules. You can pull them off, you can replace them with other ones, and you can configure them with the jumpers. So to be able to use one of these GH drivers, you have to have something like this that supports the standard step stick driver. A lot of the boards that you see right now, the ones that are designed for Creality style machines and Creality boards, are going to have integrated drivers. These have the driver chips directly soldered onto the board and they are not replaceable. So sorry to say, all the mini board users, the Creality printer users, you're not going to be able to utilize these drivers right out of the gate, but you could always swap to a different board to get that advantage. And the hardware side of this install is very straightforward. We're going to be using Log today here. He currently has an SKR3 board. It's an EZ with the blade type driver, but it also supports the silent step stick style. So let's get those installed real quick, then we'll move to the configuration via G-code. Now, just like with any other silent step stick driver like one of these, it's important to get it installed correctly. And they don't tell you exactly what all of these pins are on the driver itself, but they do give you a slip of paper that explains all of them. You want to make sure you get them installed correctly on the board, or you might cause some damage, either to the driver or the board. I usually go by the direction and ground pins to make sure I have them lined up with the board correctly. On these, the direction is R6, that guy right there, and ground is R19. So make sure you have those lined up on the board. Also, if you're using these in standalone mode, this is your VREF spot right here. So measure your current from this pin and then adjust it with your potentiometer, just like you would any other standalone driver. And as always, just like with any other driver chip, it's always a good idea to add a heat sink of some type because they can get very warm. Now, depending on the board that you're installing these on, this is an SKR2, but it's pretty much the same as a lot of the boards that we've seen for a lot of the different iterations for a couple of years. You can flip it over to the back, you can look at the drivers, and you can see which pins are labeled ground and dir. So you know which side to face that driver. Also, you will note these jumpers right here are what configure it for standalone or UART mode. This one is currently configured with that jumper right there for UART. On the Big Tree Tech boards, if you wanted to go standalone, you would populate all 4 of these bottom ones right here. That would allow you to set the micro-stepping to however you see fit. But check the manual for your board to make sure you're doing it correctly. We're currently using UART mode. So with that information, we know R6 and 19 are direction and ground. So the driver is going to install just like that. Now with the SKR EZ, these enable you to use the blade type drivers. Let me pull one out just to show you. They install vertically. And because of that footprint, you can't use the jumpers like you can on normal boards to set your mode. You can adjust sensorless homing, which we don't need to for our driver install today, but you can't use step dir mode. You have to go UART. SPI is also acceptable, but today we're doing UART. So they will work on this board, but you can't use standalone. But they would install the same way. Just like that, and since we're only interested in these drivers for the input shaper feature, we only need one for X and Y. So we'll just remove this one as well, and we'll install that other GH driver in the Y position. There we go. Now we're ready to start using our drivers. Almost. Now, up until this point, I know I've been trying to sell you on using Input Shaper with no firmware changes, and that is true, you can do that. But if you're going to use this driver in UART mode, you want to make sure you have 2208s or 2225s set up in your firmware as UART mode. If you're using standalone, it's not going to matter. You do all that configuration through the jumpers, and that should be already configured in your firmware. So if you need to change over to a 2208-2225, you need to do that now to make sure you're using the correct features for that driver set. Again, it depends on what you have been using till now, and the Easy board, they force us to use UART. So make sure you have those changes in place, but as far as input shaper is concerned, no firmware tweaks needed. Let's go ahead, power up the printer, and get these configured with the correct frequency. Now after you get your drivers installed and power up, you're going to notice that they're flashing at a certain frequency. When you see them like this, that means they haven't been configured yet. They've just been powered up. We haven't sent them any G-code to tell them what frequency for input shaper to use. So this is normal. Next, we need to head to their site and grab their calibration model. They use the same method as the manual model in Clipper. You print a model, you measure some aspects of it, you do some calculation, and then you know what to put into their configuration tool. So we'll just grab that model. When you unzip it, you'll have two different G-codes. One for XY, that's Cartesian. AB would be Core XY. And you're going to have to make some modifications to this G-code depending on what printer you have. You'll notice they slice this with Idea Maker. That doesn't matter too much. It's a very simple G-code. You just want to make sure you have all the aspects set depending on the features set you have installed on your 3D printer. Really, the only thing I have to do is auto bed level before each run because it's a Prusa style machine. So after G28, I'm going to enter G29 to make sure to do that level, and then everything else is going to be correct. Because I am running Marlin, you'll notice a lot of these commands are Marlin centric. So with that, we can go ahead and take it to the SD card and we'll run it on the printer. You'll notice when you fire up your calibration G-code from their site, it's going for PLA. So use PLA to run this test, but it runs the hot end to 210 and the bed to 50. More than good enough for this test print. And it's going to do a lot of the same things that the Clipper test print does. It runs through different accelerations, trying to test all the different frequencies for input shaper. Now when you run this calibration G-code, you'll notice after you're done with the start G-code you entered, like your home and your auto level, mine's almost complete, the printer's going to do a little bit of a shimmy and a shake. Those are the movements it's using to communicate with those drivers. So what it's doing right here is moving to 100, doing a couple of quick movements, same for Y, and then it's ready to start its testing. And we'll just let this print, and we'll see what the results look like. Our test print is done. It only took about 15 minutes. It's a very easy print to do. We'll pull it off, we'll make some measurements, and then we'll do some math. So just like the manual method with Clipper, we're just going to count these ridges here at the top. We'll measure the distance in between them. Then we'll do some calculations to get our number. So I'm just going to mark the first one, and then only go with the ones that you can see clearly. We've got one down here. So we've got 1, 2, 3, 4. And this is for X. The nice part about this is it's G-code. You can't get the model turned around the wrong way on the bed, so you know that this is for X. Now measure the distance with the calipers in between the first and the last point. And to me, I'm pretty happy with 8.2. So we've got 8.2 for X. And we'll do the same for Y. 1, 2, 3. Let's go ahead and go down to this one, 4. And for Y, I'm going to call that about 9.1. And then with those measurements, you can go into the user guide and they give you the formula you need to use to calculate your frequency. Then we can take that frequency back to their online G-code generator, and then we'll be able to set input shaper on those drivers. So here's what we came up with. X, we had 4 points and they were 8.2 millimeters apart. Y, 9.1 millimeters apart, 4 points. And then this is your formula down here. So you take the speed that you printed at. Remember, we sliced that file, 100 millimeters a second, external parameters. We edit the slicer so that it can achieve that. So that's the intended speed. Then you take your points, 4 minus 1. So it's actually 1 less, just like in Clipper. You don't count the first one. But that gives us 300. And then you divide that value by the distance. So 8.2 millimeters. So 300 divided by 8.2. That's our frequency. So for X, we're going to round up, let's call it 37. That's the frequency for X. Now Y, same thing. 100 was our speed, 4 points, so that gives us 300 divided by 9.1. And let's round up to 33. So those are the frequencies we need to use to generate our G code. Now we jump back to their calculator, and we just fill these in. So it is a Cartesian machine. Remember, you can do Cartesian or Core XY. You have to pick which file you want to use to test that. We're going to go with MZV. Try any one you want. Try all of them. See which one's the best. I like MZV traditionally on an i3 machine. And then your frequency. We're going to go with X here. Our X frequency was 37. Damping ratio, I'm not 100% sure what they're going for with this setting. I'm going to leave it as default, but I might do a deep dive on that, figure it out. We'll just leave it default for now. Start position, this is where it's going to do the movement. I just leave it at 100 because that's in the middle of the bed. You can set it however you want. We are working on X, that's the driver, and then this mode down here. Current is referencing spread cycle, so the high current mode. It's probably the best idea to use spread cycle when you're doing something like input shaping. Just given the fact that you're going to be moving at a higher speed, you want spread cycle. Now, they do give you the option for voltage. That is Stealth Chop. I do use Stealth Chop on this printer. I like it because it's a lot quieter. You can still use Input Shaper. I've done it many times. But beware of skipped layers and things like that when you're using Stealth Chop mode. But for this one, I'm going to leave it voltage. And you can generate G-code. It copies it for you, but I'm just going to take everything here and Control-C it to copy, and I'm going to save it in Notepad++ so we can use it later. Then we're going to do the same thing for Y. We had 33 as the frequency. So all the same settings, I'm just going to swap out 37 with 33 and switch it to the Y motor. And generate G-code. And I'll copy all that. You can see how it switched to Y and put it in my Notepad++. Now we have all the G-code that we need to use to be able to configure those stepper drivers for input shaping at a certain model and frequency every time we start a print. Remember, volatile memory, it's going to erase it when you turn it off. So it's just as easy to run this in your start G-code to get that input shaper configured. And just a little bit of insight on this process before we continue on. We're only doing 4 points here on this test print, both X and Y. The more points you're able to measure, the more accurate your calculation is going to be for the most part. This test print is only a single wall. It's actually kind of difficult to tell what's going on here to be able to get a good measurement. I might try a different part, maybe the one for Clipper here in a moment, just to see if it's any better. But the more measurements you're going to get, again, the better off you're going to be. I'm just doing this to show you the process. If I was trying to nail this down accurately, I'd probably try to get a better measurement with more samples. And there's one other little piece you need to be concerned with setting up these drivers. Based on how these drivers are configured before every print with the G-code, the drivers assume for X and Y, you have 80 steps for 1 millimeter set. Now, not every printer is going to have that, but the easiest way to get around it, to use that 80, is to just set it temporarily while you're doing the calibration before every print, and then flip it back to your usual. Log is currently set up for 100 steps per millimeter in X and Y, and it's just based on the pulleys you use for your printer. 80 is probably the most common. You can check that either in Marlin with an M503, or you can usually see it from your LCD screen in the motion menu. So to test our input shaper settings, what we've just calibrated, I'm just going to use that same test print. It's quick, I know it works. So I'm going to replace the G-code that the default calibration print uses to turn off the drivers, basically, to reset them to 0 for X and Y. And I'm going to do an M92, remember we're running Marlin, X80 to set that motor to 80 steps per millimeter for the calibration tests. And then I'm going to paste in the X values from the calculator that we used online. I'll just copy all of these and paste it right here. And then right after that, I'm going to do the Y. M92, Y80. And then I'll paste in our Y values. And then when we're done with those calibration movements, I'm just going to do M92, X100, Y100 to return us back to our steps per millimeter that we usually run at. And then I can just resave this calibration print, take it over my printer, and run it again. So I restarted the printer just so I could show you this. Remember, the flashing lights on the drivers are telling you what state the drivers are in. Right now, power's been cycled, they have no configuration. Let's start the G-code, and then we'll take a look at the flashing light after they're configured. And just like before, after our bed level, it's going to start processing that start G-code that we put in there to set our frequency for the drivers. It's going to go to 100. It's going to do some specific movements that tell those drivers to set it a certain way. And then Y for the same way. And now the drivers are set. Input Shaper is on. And we'll proceed with our test print. And you know that the drivers got configured successfully because they go from a half a hertz to a full hertz flashing. So it's just a little faster than when it's not configured. That's what you want to see right there. If it's flashing any faster than that, you probably have a problem, and inside the manual it will tell you what those errors mean. And if you're going to make this a permanent setup, we built our G-code manually, but you just add this to your start G-code in your slicer. So if you're using Prusa Slicer, you go into Print Settings, Custom G-code, and right before your print's ready to start, you just paste in the G-code that we created. So mine, for example, I'll just grab the X, I'll set my motors, M92, X80, Y80, paste in my X G-code, paste in my Y G-code, that will configure the drivers, and then we'll M92, X100, Y100 to flip back to my usual setting. You'll save this, and then every time you create a print, when you slice, it'll have this in here ready to go to configure your drivers and start using that input shaping. Our test print post-driver install is complete. Let's see how we did. Now remember, the calibration on this, I did it really fast and loose. I could probably get this dialed in a lot better, but I just wanted to show you the process of how to get this done. So this is before, this is after. Now you can still see some artifacts here on X, and kind of some weirdness down in here, but it's definitely an improvement compared to the before. Kind of watch them from the side here, see just how rough that was, and then after. You can definitely see it down here in the arms of the X. And then we'll shift to Y. Again, before, after. I think Y was even a better improvement. Maybe I got that one dialed in just a little bit better than X. But you take a look at the side, just how rippled this one is versus the after. Much cleaner. You can really see it on the ghosting on the Y before and after. So they're definitely doing their job. And because I actually do like doing the testing for these videos to see the before and after, I wanted to run you through a couple more scenarios. Now this one, remember I told you have to run that M92 to set it to 80 steps per millimeter if you have a different setting. I have 100. Now we didn't do that on the first print. That's this one here, the one we dialed in. It was set to 100 the whole time. So I wanted to go back and confirm and add an M92 8080 to the same G-code and run it again. Now, it's really hard to tell here, but if you look at it with the naked eye, they're exactly the same print. There was no difference in between having the M92 and not having it. Now, I did confirm running that G-code that they give you in the calibration print, all it does is set those drivers back to default. I checked the drivers to see if they were blinking. They still were. It just makes sure that there's nothing set already on the drivers before it starts your calibration. So no harm there. You really don't need that M92 on the initial calibration. Then I got to thinking about that single wall part that they use in their calibration. I think it's kind of hard to tell what's going on with that resonance in that single wall part. So I took the clipper part and I re-sliced it to be able to use it in this calibration method. You can see all the resonance there. I think it's a lot easier to measure this style of part, all those different ripples. You can see the X side here. So I ran that. There is a link in the description to the file that I used to get this done. I had to set it up so that I could escalate through accelerations 5, 1000, 1500, all the way up to 6000. So I just ran this part with no settings, no input shaper settings at all. And then I took the same values that we got from our last part, and then I ran it with input shaper on. So there's Y. You can see how much of an improvement. Again, I use the same settings. 37 for X, 33 for Y. You can see a lot of the belt in here. That's probably more due to the printer than anything else. But all that resonance is gone. So it's still in effect. It did its job. But you might consider trying this part as well, rather than just the default part, to make it just a little bit easier to measure. See if you come out with a better frequency number than you do with that stock part. So there it is, the GH Enterprise Smart Shaper Silent Step Stick. And as you might have noticed, these are geared more towards a 3D printer running Marlin firmware, because that's where you're going to get the most bang for the buck. We haven't always had the ability to use input shaper inside of Marlin, and given the fact that you can run these in standalone mode or UART, you can take any old 3D printer board that has replaceable drivers, plug these in, and start using input shaper right away. No firmware changes for the most part. Also, these are around $40 US for a pair, and that might seem kind of expensive, but if you take into account the price of a 2209 and maybe having to run Clipper, you might need a Raspberry Pi or a board that's specifically designed to run Clipper, this is going to be pretty affordable. Also, with input shaper altogether, this is how I'd like it to be done, personally. I'd like it to be closer to the chip, just given the fact how input shaper works. I think living on that step stick board is the correct place for it. And I hope to see that going forward. We'll see what the driver companies do. I did mention there is a Marlin branch where you can control these with G-code. I think that's going to go right in line with all the different firmwares. We'll be able to control them directly, and then we won't have to mess with all this firmware. So I really look forward to see what happens in the future with things like this driver. That is it for today, and I'll see you really soon on the next one.